All right, what's up, everybody? Welcome to Earth Science. Time for some more new stuff. I'm going to start with what you are going to think is overly simplified. And in fact, it's something that I guarantee you've noticed multiple times in your life. And it's going to be something that a bunch of us get wrong in a quiz. Historically speaking, maybe you guys will be the group that breaks the trend. I'm going to, here in my classroom, turn on the sink, point my hand, there we go, point the camera there, get my hand wet. And if I start to shake it here and it dries, if water evaporates, you tell me, what sensation am I feeling on my hand right now? What's happening temperature wise as that water evaporates? We'll use a paper towel for the rest. All right. Same thing if you jumped out of the shower, last time you jumped out of the shower, or a bath, or like it is on this thing, a swimming pool. What do you feel when water evaporates? I heat with wood, so the house is pretty cold in the morning. So getting out of the shower sometimes when all that water starts evaporating, it can be shocking, right? So we've all had that experience. What do you feel when you get out of a pool or bath or shower, pond, lake, rainstorm? Mouse doesn't feel like working this morning. I guess wet hands. We feel, cold. Hopefully your computer's working better than mine. All right. So that's a critically important neuroscience relationship to get. That's of feeling cold, right? So that's why I put a big star right here. I'll switch to this tool and see if it works better. And that idea is that when water evaporates, temperature decreases. All right. If we got more into the latent heats of water, which we should, but maybe not during the year of COVID, it takes heat energy to get water to evaporate. So when I was waving my hand in the wind there just to make it go faster, it steals heat energy from my hand in order to evaporate. So I feel the sense of cold. All right. So somebody very clever. Oh, there it is right there. That's why I said this. Heat energy released during gain. Okay, so here you go. Heat energy gained during vaporization. Vaporization is evaporation for all intents and purposes. So the water needs to gain that much energy in order to make that work, which is why I feel cold, because my hand is giving that energy to the water. All right, so we can use this idea. This is called evaporative cooling. Oh, I spelled it wrong. Good thing I didn't say here, spell it me. Oh, maybe I didn't. It just isn't a word. Evaporative. Yeah, I think that's right. I'll blow this up. I know sometimes this is too small. Evaporative cooling. So somebody very clever came up with a way to actually use this to calculate, to measure how much moisture is in the air. So let's consider two different situations with junky generic clip art from the internet. Desert versus jungle. So guess what? It's very dry here. It's very humid here. Okay. No duh. That's not a surprise. So if I were to do that thing, get my hand wet and then move it a little bit, or if I were to just take this beaker, fill it with a given amount of water, and chuck it on the ground there and watch and see how long it takes to evaporate, which one of these two is going to have more evaporation? Hopefully you guessed right. More evaporation happening in very dry areas, and less evaporation happening in very humid areas. Therefore, if we think about the idea of how much is going to cool in this evaporative cooling thing, like people in deserts actually use this to cool their house. If you have a source of water that's I won't say inexhaustible, because no water supply is inexhaustible, but if you have an abundant source of water, people will there's roofs that just trickle water on it, and then as that water evaporates off, it cools the house. That's a thing. So this idea of evaporative cooling then would be that because it's so dry there, because there's more evaporation, there's also more evaporative cooling. Whereas if it's humid and there's less evaporation, there'd be less evaporative cooling. Okay. So there's a way that we can be clever here and come up with a way to actually measure the humidity in the air using that relationship. Basically, do you want to say drier or more humid? Let's go drier. The drier it is, because we could say this exact sentence with the opposite words and it would still be true. The drier it is, that means the more water will evaporate, and that means more cooling happens. Or we could have said the more humid it is, the less water evaporate and the less cooling happens. So somebody very clever said, I think I could use that idea that we've all experienced, again, that idea of evaporative cooling, that idea of your skin feeling cold when water evaporates. I said, I think I could use that to actually measure how much humidity in the air. Now, if you've been in my room this year, I don't know if you've noticed this thing on the wall, but here's what we got. We've got a thermometer. This is going to be hard to hold. Thanks for your patience here with my rookie YouTube skills. We've got a regular thermometer, and then we have another pretty much regular thermometer, but the one exception to that is that it's got this, it almost looks like a shoelace. It's got this like cotton string that's hollow that goes down into a little plastic tub of water. So what happens there is that water slowly evaporating. Now, I haven't been to school in 2 weeks. I just filled this up about 5 minutes ago, so I'm not sure it's going to be working perfectly. I don't think we'll actually do the numbers yet. But let's think of the theory behind this. If water's evaporating off this little wick, that means that the temperature on this thermometer is going to go down, evaporative cooling, right? If it were really dry in here, it's going to go down by a lot. So if I looked at these two temperatures and I saw that there was a large difference between them, I would say, wow, a lot of cooling has happened. Therefore, it must be very dry in here. And then, if this doesn't terrify you, look at all those little numbers on that thing. I won't get too close. Then we can actually take those two numbers, put them in there, and we've figured out what numbers relate to what humidities and calculate exactly what the relative humidity is. If the two were about the same, we would say, okay, not much evaporative cooling is taking place. That means the air must already be pretty humid. There's just not evaporation taking place like the jungle up above here. So that wet, we call this the wet bulb. That wet bulb temp is not going down by much. It's humid, right? So it's like that simple idea. It's always remarkable to me every time I talk about this. That simple idea that you've experienced when you got out of a pool for the first time, out of a shower for the first time, out of a lake for the first time. That has led to that device, which, you know, works really, really well. It's called a psychrometer. This is the contraption right there. I think today, I don't want to go too fast for everybody. Hopefully air masses and all of that went okay yesterday. So I think today maybe let's hold off on learning exactly how to calculate these, and maybe I'll try to write up a couple questions that will deal more with like the theory behind this thing. But this is called a psychrometer. Psychrometer. It's kind of a mouthful. Internet says that's wrong too. But that's right, I promise. And again, a very simple contraption where we have a dry bulb, bulb, like light bulb. That little ball at the bottom of the thermometer we'll call the bulb. And then a wet bulb. Right? So how does it work? Get the wet bulb wet. Dry bulb must stay dry, otherwise it's not a dry bulb, right? Spin using the handle, water evaporates, and here's the important theory, the important relationship behind it is that if the wet bulb decreases by a lot, it is dry. Or opposite, and I'll write that, your call if you want to write it. If the wet bulb decreases a little, it is humid. All right. Because in humid air, there's not as much potential for evaporation. Not as much water is going to evaporate. The wet bulb doesn't go down as much. And then some folks, and this is where it's going to get like to be, okay, that looks a little intimidating. And it can be a little tricky. There's going to be some hard parts to this. Some, I won't even say calculations. It's more like logic and then using this. And if you've ever played Battleship, this is the premise of it. Like, in Battleship, you say like, what, B7, something like that. I don't know. It's been so long since I've played it. But you go like, okay, over to the B and then down to the 7, and nope, you missed. This is the premise of that game, I think, right? So we'll figure out how to do all the math on this, but I think we'll save that maybe for next week. So yeah, but let's think about the theory behind it. That thing right there, humid versus dry days. Sling. Sometimes we'll call that a sling psychrometer. Like this thing right here would be the sling. And you whip it around to help the evaporation take place. The one nailed to my wall, obviously that's not the case, but yeah, what do you think? Sound good for today? All right, hang in there, everybody. We'll talk to you soon.